And next, we're very fortunate to have Dr. Katja Hofmann from Microsoft Research. Katja is Senior Principal Researcher at Microsoft, and today we'll be giving a talk that involves two main scientific breakthroughs of the AI revolution. One being game playing, reinforcement learning, and the other being generative AI and sort of auto-regression. So as a cognitive scientist, I'm really interested to hear what Katja has to say about how we can integrate learnings from studying how humans play computer games into building better generative agents. I have to say there's an element of my 15-year-old self that feels sort of like all of that time playing GTA 4 and those games is finally going to good use advancing scientific knowledge. So let's welcome Katja to the stage. Katja, we're looking forward to the talk. Thank you.
Thank you so much. Thank you so much for the fantastic introduction and for inviting me. It's a pleasure to be here. And maybe with a nod to that 15-year-old self, I just love this picture here, where my team recently came together in a hackathon, where one, we got to play video games for work, and two, we got to probe a generative AI model that we had trained on a very large amount of human gameplay data. And there is something magical about going into this prototype system and trying to figure out from scratch in such a neurally generated interactive environment, how do all these things work that we're now expecting from language models? What does prompting look like? What kinds of results can we expect? How do we push the limits? And how can we develop a better, more systematic understanding of what these kinds of neurally trained simulators can do today? So a lot of my talk is going to be exactly about that. Thanks also so much to Tim for introducing this concept of neural simulators. So I won't have to do quite as much setup in the talk today. But just in case you're not yet convinced of the idea, I want to show you, just start with a clip of what is possible today. And let me see if the video actually plays. Here we go. So what you're going to see is a clip that is entirely generated by our neural network model, no game engine under the hood, and so I hope this gives you a sense of what is possible today. We can train a model that is able to simulate not just 3D environments, game physics, it's also able to capture, for example, the multi-agent interactions within this game, which was something quite difficult to achieve. So very interesting to see what's possible there today. But now, given the state of the art, of course, there's a lot to do. There's a lot to improve. The resolution of these are currently limited. The memory or context length is limited. At the same time, we are convinced that the technology is advanced far enough to start to dig deeper, to ask questions about how can we actually make those kinds of simulators useful? How can we use them to empower, for example, creators? And a lot of my talk is going to be about this. We're not primarily focusing here on learning a world model that is then used to train AI agents or to make things faster. We've primarily focused on trying to understand where is this technology leading in terms of what it can mean for their human users. So imagine you're a game creative. You have released an awesome video game. People are playing it. There's limited content in there, so within a couple of weeks, all the key fans have played through your content, and they keep asking you, can I get a new map? Can I get a new character? Can you introduce some interesting new game mechanics? So what do you do today? Today, using traditional game development techniques, this means that you start a collaboration within a team that represents a diverse skill set, visual artists, animators, programmers. You start maybe with a few hand-drawn prototypes. Maybe you use DALL-E to create some concept art. You start to explain the idea. This is what this new map could look like. You work together with the team, and after a couple of weeks, you have a first prototype, a version of what it could be like to have this new map in your game, and you start playing with it. The question that we asked here is, could we use these kinds of environment simulators in order to empower creatives to directly work with this new medium in order to develop new ideas? And what are the kinds of capabilities that these AI models would actually need in order to truly support these types of creative processes? In order to start getting some answers on this, Linda from my team and others ran a fantastic user study with creatives in order to understand, one, the degree to which they are already either thinking about using generative AI models or have adopted generative AI into their workflows, or B, what kinds of aspects might be stopping them from fully utilizing these kinds of tools today. The team did this by introducing a design probe called Cygnus. A design probe is a works like prototype, so there's no actual AI under the hood, but it's set up, coded in Unity, in order to mimic the kinds of AI capabilities that we might expect to emerge over the coming years. And the team did a fantastic job here on making this very broad. So for example, the prototype would allow people to explore what it could mean to provide text input to generate an interactive environment, or what it could look like to take some visual examples and use them to introduce, for example, new gameplay mechanics. And so starting from this design probe, they then had a discussion with groups of creatives to try and understand, well, in this hypothetical future scenario, what would you worry about? What are the kinds of things you would want to do? What are the kinds of things that might limit you using your understanding of what's possible today? The workshop protocol, as I mentioned, was the simulated walkthrough of Cygnus, as well as then this discussion. And it's also really interesting to look at the participants in this study. Sorry, there's something wrong with the clicker here. I'll just go here. There we go. The team went out of their way to try and involve as diverse a group of professionals as possible, covering, for example, representatives from AAA studios as well as indie studios, looking at the geographic distribution of the people we collaborated with, as well as including teams of creatives with disabilities. And so that provided a really nice, broad understanding of what these creatives were thinking about. To give you a quick sense of the kinds of things they were mentioning in the study is, one, they really emphasized that they needed to explore how to visualize creative abstract ideas. They noted the problem of not knowing where to start, basically needing some kind of initial prompt for themselves that would allow them to then iterate. They very explicitly talked about mixing and iteration, as well as the idea of directly coming up with something new while being immersed, while playing the game. And so the two main themes that the team pulled out of all these interviews with these creatives were two main aspects that are actually well known in the creative computing community, but which haven't received that much attention within the AI community, because people are speculating here. People are so focused on training the next biggest, best model that they don't really pause to ask, well, what are the capabilities? What kinds of things do we actually need to support as we drive development of those models? And so the two key things that emerged here were, one, support for iterative practice, the practice of being able to start from everything that you have created before, iterate, remix, as well as support for divergent thinking. So being able to work with a model that supports broadly exploring a space of what's possible within that medium. And so from this understanding of what creatives needed, we then went back to our AI model and tried to understand what AI capabilities would be needed to support iterative practice and divergent thinking, and then develop an evaluation protocol to understand how we could actually measure whether we're making progress towards those capabilities, and finally looking at the degree to which our generative AI model matches those capabilities. So the first AI capability required for supporting iterative practice and divergent thinking is consistency. If you have a model that is not capable of capturing the 3D geometry of your map, the underlying game physics, how characters move, how the game responds to key presses, then that really limits the degree to which this is useful for creating something that might actually work within the game. So consistency is the first key aspect here. The second one is diversity, and so this is quite natural directly from this understanding that we need to support divergent thinking. A model needs to be able to generate and capture the full breadth of what's possible within a game. And the third one we call persistency, and by this we mean the ability of the model to persist user modifications to the input. So think of this as, what does prompt engineering look like within the visual space of such a game model? And as I go into the model now and show you its capabilities, I will go through in detail how we evaluate those, and I'll show you examples of what the model here is able to do today. But so first, let me tell you a little bit about this generative AI model, how we trained it. And of course, this all starts with the data that we have available for training. In this particular scenario, we were in a very lucky position to be able to work directly with the game studio, our colleagues at Ninja Theory, at a Microsoft game studio directly in Cambridge, and their title, the game Bleeding Edge. And just to give you a sense of that game, it's a 3D video game released in 2020 on Xbox. It's a team-based game. So here, for example, you can see a team has just jumped to this map. There's an aspect of resource control. One goal is to collect these power cells that you just saw. And it's a competitive game. So for example, here you see two teams fighting against each other. And our character is actually a healer. So you see it providing support for its teammate here during this combat. So pretty complex 3D game environment. And our goal was to be able to train a generative model of this without any game-specific information. So the only thing that we wanted to give to the model is, one, the visuals that were on the screen, and two, the actions. And in contrast to Tim's work, we actually did have access to the controller actions here, and we believe this is quite key to our ability to train a highly consistent gameplay model. We worked together with Ninja Theory, following responsible AI guidelines, to unlock a large amount of human gameplay data for us to train on, and this resulted in a total of 8.6 years of continuous human gameplay that we're using for the models that I'll be showing you today. We have access to even more, but it was trained on this subset, and this corresponds to a total of 1.6 billion images and controller actions. And again, we think of this as the human interface, literally what the player would see on the screen and the button presses they have on the controller. Now, with this data, the model that we trained and the design decisions that we made were really focusing initially on scalability and consistency. And by scalability, I mean that we wanted to ensure that we have a model with minimal inductive bias in such a way that we know that as we scale up compute, as we train this more and more, the model becomes strictly better. And by consistency, we meant that we were focusing on trying to get a model where we would be able to continue generating gameplay that is consistent with the underlying structure of the game, 3D geometry, character movements, etc. In order to achieve this, we focused on well-understood building blocks, very similar to actually how a large language model works today. First, we needed to make sure that we can express the game visuals in a symbolic or token-based representation. We use this by training an encoder-decoder model that learns a compressed representation of the image. That gives us, then, when we encode an image, a symbolic representation that we call the latent representation, indicated by Z. And we also compress the actions, any aspects of the controller that are continuous is discretized, so that we arrive at this discrete representation of the visuals and the controller action. Then we train a transformer backbone, so the workhorse of scalable predictive training. As input, we provide this compressed representation of the image, followed by the next controller action, followed by the next image. So you can see this really as we input the sequence of gameplay that we have seen up to a given point. And then we train this model in a predictive way, meaning that we ask it to generate the next token, the next symbol. For example, here, this is the next symbol of the next controller action. And then we simply train this based on a predictive loss. So if it matches what we've actually observed in the gameplay, then we may not update the parameters of the model. And if it makes a mistake, we backpropagate, we update the model. And so with that, we get a model that is scalable and that keeps improving its predictions as we keep training. Now, from this simple predictive training, or if you will, pre-training, what are the kinds of things that emerge and that we can do with the model? Because we use the model to learn to predict both visuals and actions, we can use this in at least 3 interesting ways. The first one is behavioral cloning, which is related to reinforcement learning that was mentioned earlier, but it's in a way the simplest possible way in which you can get a behavior out of a machine learning model. It means that we prompt the model with visuals taken, for example, directly from the game, and we ask the model to then produce the next controller action. We feed that into the game, we get the next visual, and in this loop, we have an agent that can actually interact with the game to a certain degree. Secondly, we can use the model for world modeling, and this is very much the mode that Tim mentioned there earlier for Genie, for example. This is the opposite. So think of this as we start the model with the visual, let's say from past gameplay that we have collected. We then provide the controller action, so that could be someone directly sitting there with a controller and playing with the model, or it could be the controller actions from the historic gameplay that we recorded. And then we ask the model to predict the next visual. So how would the game evolve over time, which is really the simulation of the game engine that we mentioned before. Finally, we can put everything together, and we've referred to this as full dreaming, because here the model is started from either a blank screen or a visual from the game, and it generates everything. So it generates hypothetical gameplay sequences of how the situation might evolve over time. Now, let's take a look at how well this actually works. In this slide, I'm first going to show you a clip of ground truth. So the ground truth is the actual recorded gameplay from a human player playing within the game engine. You see here a character called Azrael just destroyed a fuel cell, moving up the stairs, and this character has a special flying mechanic, so you can see it here, spread its wings and crossing the path to the other side of the map. And now, in this demo of what the model is able to generate, this was really the first time we believed that there's something interesting there as a team, because it's just so fascinating to see how the different, how the understanding of the different parts of the game mechanic evolves over the course of training. After 1 day of training, I am now taking the model, feeding in an initial 9 seconds of, an initial second of real gameplay, the visuals and actions, and then I'm taking the actions from the actual human player, so the same actions as we saw in the ground truth, but all the visuals are generated by the model. And so the closer the model matches the actual ground truth, the better its understanding of the game mechanics. So after a day of training, initially this looks quite promising. Some 3D geometry is captured, but we see that long-term consistency is a problem, and the quality of generation here deteriorates as we continue to generate gameplay autoregressively. So that means from that initial clip, we keep feeding what the model has generated back into the model, and you can see that over time, the quality here deteriorates. After a week of training, things are looking more promising. We see it destroyed the fuel cell, moved up the stairs, but it hasn't captured the flying mechanic yet. And so you see here that the model actually simulates gravity correctly because it hasn't yet understood that this character can fly. Finally, we continue training, and after a month, everything looks quite promising. 3D geometries there, interactions, and we have the flying mechanic finally captured there as the character moves across to the other side of the map. Looking at some numbers, this is a plot of how we can quantify this quality, consistency, as we continue training and across different model sizes. And so here, the most pink and the furthest to your right curve is the largest model that we had trained at the time we took the snapshot, so a roughly 900 million parameter model. The quality here is measured in terms of FVD, which is a video quality score. The lower, the better. And it essentially tells you how close we are to the ground truth. So you can imagine that there is stochasticity in the game. We cannot necessarily predict where all the other opponents and our teammates are going to be. So there is a lower limit to how close we can get to the ground truth. But you can see that we're approaching this very closely. And anecdotally, we find that below a score of 100, we get to this high-quality, long-term consistent generation that I showed you in the example earlier. So that's consistency. Hopefully, I've now convinced you that with this kind of model, we're able to train a model purely from observing human gameplay that is able to understand the mechanics of the 3D environment and the physics to a degree that allows us to create consistent generations of that gameplay. Now, how about diversity, the other criterion that we mentioned earlier? I just want to give you a simple example here. If there are 3 possible paths within a given scene, we want to make sure that the model captures everything that is possible, everything that would be of interest to a human player. And so just as a demonstration here, indeed, our model, when started from the same initial starting point, is able to generate the potential continuations going left, right, or center from exactly this branching point. We can also quantify this a little bit more, and here we've captured this in terms of a distance, the Wasserstein distance, from the distribution over actions that were issued by human player. And we can see that over time, this curve goes down, and we approach the true distribution of actions that would be issued by human players in that gameplay. So we're making good progress towards capturing meaningful diversity within the game. The third capability I want to mention is persistency, and I find this the most magical and fun to explore. This was also one that was really fun during the hackathon, of which I showed you that picture earlier. As I explained earlier, by persistency we mean, can a creative actually work with this kind of medium? Could they introduce new game elements, probe what it would mean to modify gameplay in order to indeed come up with the new gameplay ideas that I mentioned earlier? As one example, here you can see that we've taken an original frame from the game and we modified it by introducing a new element, a power cell, in a place where it usually wouldn't occur. From the starting point, we feed this initial prompt into the generative AI model. And now, of course, the interesting thing is what happens. And we see that not only has the model persisted this element, it also understands that this is something that the player can interact with. And it generates both the attack action of the player as well as the consequence of actually destroying and collecting this resource. This doesn't stop with static elements. We can also introduce additional characters. For example, here, we masterfully photoshopped a character into this original game frame. And again, let's hit play on our generative model and see what happens. We need to be careful with too many characters in here. This one defeated our own character rather quickly. Let's take another scene and, again, masterfully Photoshop a character into the scene. Let's see what happens here. Oh. I do like this a lot better. So these were examples of persistency. We have just started to scratch the surface of what's possible here, but I did, again, want to give you a quantitative understanding of where we are in terms of persisting user modifications or creatives modifications to our gameplay and scene. And so here in the table, you see a few interesting things. First, that we initially are able to persist players or opponents with at a higher rate than, for example, these power-ups. Initially, when we condition on just a single frame, the power-up persistence is only 14%. The one for players, 55%. But very interestingly, persistency really increases when we provide more of that initial sequence. When we go up to just replicating the frame 5 times with that modification, we get to a very high percentage of both usable generated sequences. We get to a power-up persistence of more than 80%, and players are correctly persisted more than 90% of the time. And so interestingly here, these are also some initial glimpses of in-context learning for these kinds of generative AI world models, which hasn't been explored as much yet in this visual space, but it's a really interesting direction to explore more. And in fact, we have one of our research interns currently working on exploring this. As I start to wrap things up, and this is almost the last you'll hear about WHAM, our World in Human Action model, I just wanted to highlight 2 further directions that we've seen within the team. The first one is looking at scaling laws. And this is work that Tim Pierce and Tabish, who is sitting right here, so if you have complicated questions, ask him, not me. So Tim and Tabish were driving this work over the past couple of months, and this is currently work under submission. Just the glimpse that I want to give you here is that understanding scaling laws is of course very important, and we've seen a lot of influence of that on how language models are now being developed. They replace the black art of coming up with model parameterizations for a given amount of compute and for a given amount of training data with some actual systematic understanding of how to make the best possible use of the resources we have available. And so it's been extremely encouraging to see that we can indeed derive very similar scaling laws when we look at these kinds of models, both in terms of world modeling as well as in the behavior learning or imitation learning that I mentioned earlier. And so I'm very excited to see this piece of work that indeed goes beyond that very naive understanding of bigger is better in this kind of scenario. An interesting twist here is that scaling laws for the world modeling aspects of these models emerged much more straightforwardly and naturally than those for behavior. But we did indeed find that with appropriate modeling choices, we can recover scaling laws for imitation learning. And so, as mentioned, I leave it with these, maybe with this sneak preview. And if you're interested to hear more about the work, I encourage you to speak with Tabish or myself afterwards. The final piece of work that I wanted to highlight is on diffusion for world models. And this one is super fun because this work actually started as an internship project in my team last summer. On the slide here, you see Ilwa and Adam, who were both interning over the past summer in my team. And this work really started from the question of, well, we've made a big bet on autoregressive models, and within the community, there roughly seems to be this split. I don't know whether it's half, but some portion of people bet on autoregressive models. And we've seen that with these models, for example, with WHAM, we get an ability to create, indeed, this highly consistent gameplay, which we hadn't seen anywhere near this with diffusion models at the time. There's this big other bet on diffusion models, and for example, video models like Sora are betting on this technology. But the ability to generate consistent gameplay indeed seemed to be very limited at the time. So this is a paper that was just accepted as a spotlight at NeurIPS, and it starts to close the gap. It makes a big step towards, indeed, training diffusion models that allow for a higher degree of consistency than was previously thought possible. And I don't think I have time to go into the details, so again, happy to chat about this afterwards. I just want to highlight that the focus here in the paper was on Atari, the previous state-of-the-art of training reinforcement learning agents for Atari in a past world model called Dreamer V3 is outperformed by a large margin when training agents here within the Diamond diffusion model. So very, very encouraging results for consistent diffusion models. and something that the team just put together over the past couple of days in response to a game engine is to prove that, yes, indeed, you can run, not Doom, but in this case, CSGO on this diffusion model, and you can play it directly within the diffusion model, as demonstrated by our top player, Tim Pierce, here in this example. So what's next? I've showed you progress that I personally find very exciting, very promising, in learning simulators that capture very complex 3D environments purely from observing visuals and interactions with those. A lot of things have started to work, and at the same time, there's a huge list of open problems. I wrote this down in just 10 minutes yesterday, and I could go on and on. The list of open problems here is virtually endless. So just to give you a small taste, let me pick out two of those. One that very naturally follows from what I showed you is, of course, understanding those trade-offs between the capabilities of diffusion models and autoregressive models. So diffusion models tend to give us beautiful high-resolution images, but they do still have limitations in terms of producing long-term consistent gameplay. Is that a fundamental trade-off? Do we ultimately need architectures that combine the best of both worlds? Or is it possible to imbue the capabilities of one or the other in the alternative type of approach? And let me pick out one more. Efficient planning in world models is a key question if we want these to be useful, for example, to have embodied systems figure out how to solve complex problems without having to simulate hundreds, thousands, or millions of interactions with this world model. Ideally, if we're able to directly plan in those, that would really be a breakthrough in terms of getting to the right behaviors that we want in embodied AI. And an area that I and many others on the team are also particularly passionate about is that aspect of human-AI interaction. I started showing you the motivation for, well, we can learn these simulators, these kind of generators of gameplay scenes. To what degree can they already start to be integrated into creatives' workflows? And could those give us the capabilities that empower creatives, that allow them to make their own the most human aspects of their work even more human, rather than thinking about generative AI as purely something that is for efficiency and that is making us faster. So very curious also to keep understanding those human AI interaction aspects and how to build workflows that really empower their users. So I leave it here in terms of open problems. I just wanted to finish on highlighting the fascinating work that our research interns are doing within our group. Our current interns are Maria and Chen-Tian, who are focusing on training multimodal models as well as in-context learning for these kinds of environment simulators. And if this sparked an interest on your side, we do have openings. We're currently hiring for a postdoc or AI researcher equivalent, AI resident 2-year position, and we'll be opening our research internship postings very soon. So if you're interested in any of those, do catch me after the talk. And with that, I'm very much looking forward to all your questions.
So any questions for Katja? Yeah.
Hi there, Katja. Thank you so much for that. I was really interested in your point about the interaction between humans and AI, which is my research area as well. And when you talked about empowering creatives, are you thinking about elements in the software itself, or are you thinking about the psychological and environmental conditions of the creatives, or are you considering both?
Fantastic question. I think within my team, we've been thinking about it more from the perspective of the AI model capabilities, so similar to what I motivated earlier. So understanding the kinds of design patterns that would need to be supported by these AI systems in order to truly empower creatives. The psychological environment is something that honestly, I haven't thought much about or don't have much expertise in, so I'd love to catch up afterwards and learn a little bit more about your thinking there. Thanks so much.
Hi, hello. Thank you for the presentation, really loved it. One question, I noticed that when displaying the persistency feature, you introduced new items that were already familiar to the model that were in the game before. So I'm kind of curious, what would happen if you showed something that was weird, never seen before? How would it react to that?
Fantastic question, and something that we're very interested in, and we've only scratched the surface of what's possible there. So let me start with where we are today. The model that I showed you, the largest model that we have, was trained on 7 maps, which are all the maps that are available for the game Bleeding Edge. And so we see within that we can mix and match. For example, we can shoot portals into the space and jump onto a different map, which wouldn't be possible within the game. So there's quite some flexibility there. But of course, as you mentioned, all the elements there are known to the model. We also have a model that was trained on just 1 map, and so we can see what it does when we start on a map that it's not familiar with. It does something useful. It keeps kind of generating sequences that are consistent with the 3D space around it. And then when you go through a door, you find yourself onto the map that it knows. So it makes very clear, obvious mistakes, but it degenerates in a graceful way. The thing that I'm really curious about is what happens when you start training across a large range of games. So how many game titles, how many 3D games do you need to train on before you get something that could generalize, interpolate between everything that you've seen, where not everything that you do has to look like a game of Bleeding Edge. At the moment, when we feed in a screenshot from Minecraft, it just keeps replicating that same screenshot of Minecraft because it doesn't know anything about the game mechanics of Minecraft, so everything is just standing still. Again, understandable given what we've trained it on, not necessarily what you would like in the long term. I'm actually quite hopeful that that kind of generalization across games is possible, also in no small part due to Tim's and his team's work on Genie, where they took a wide range of platformer games and they showed indeed signs of life of being able to create this generic platformer game engine. One key limitation, as you can imagine, is the data. Can we responsibly source the data that is needed to train on? But we think we're making some progress on that. So stay tuned for any new results on that.
One more question? I think, yep.
Hello, nice talk. Thank you very much.
Thank you.
And I want to dig a little bit more about the world model and the mechanism you just talked about, say, data limitation. Because I can imagine, say, for example, a 2D flat play game, there's no way to generalize if you're only training on image data, or at least now I'm aware of that. So my question is that when you train on RGB data or sequential, video data, there's an underlying mechanism, say, game engine, trajectory planning, meshing, rendering. Are they all needed to be trained on this world model? Or do you think there's a deeper mechanism to generalize them more, to extrapolate? Say you only have 1 game, maybe you only have 10 frames, and then you somehow generalize to more of them because you somehow figure out underlying behind the game mechanism rather than just RGB data. Is there any thought of this kind of future direction? Thank you.
Very interesting question. And I think what you're getting to here is there some kind of internal representation, maybe something that's already used in game engines today that could be in a way that lingua franca between different game titles. The reason we made a big bet here on just the human interface, so working purely off of the 2D images and controller actions, is that we think of this as the most universal way of interacting with a game. No matter what game engine a game was developed on, a video game has visuals and it has control actions. It also has audio and other modalities which we haven't considered here, but this seemed to be a subset. And we were convinced that if we can make progress on this, if we can show that there's no game-specific information, no information about explicit 3D geometry here, then that is a very exciting proof point because it means that in other 3D environments, we might be able to do something similar. We might be able to have models that capture the underlying geometry, structure, mechanics, physics of those 3D environments even with data that can be obtained quite easily compared to, for example, mesh data and other structured 3D data that is usually much, much harder to get at scale. We've gone back and forth on what kind of additional representation could look like. At the moment, from everything that we understand about the representation learned here, there's no easy way to decode the structure from the latent representation. We haven't been able to use, for example, linear probing to decode specific elements. So any additional information about how this maps to, say, 3D structure would have to be considered and trained into the model. I'm currently quite drawn towards keeping this as general as possible. So could that interlingua be natural human image? Would that be a way to impose additional structure onto this without going all the way to something as expensive as 3D meshes? But whether we're able to succeed with that's still an open question. So the jury's still out on that. Thanks.
Okay, let's thank Katja again. Thank you, Katja.
Thank you. Thanks.
Wonderful talk, thank you. So now we have a 15-minute break, so feel free to go out, get a coffee, and then we're going to start back at 11:05 with the panel before lunch on how should we fund AI research. So thank you all for the questions and staying engaged.